So if you guys understand what this is, then there will be no need for the next lectures. Once we understand what is inside the next lectures are just there's nothing to it. Only forget about it. Forget about the second one. Only this one. Pardon? So as I said, I think in the last week or the last week, I said that what each computer or each CPU is designed or has what is known as the ISA, the instruction set architecture. So each CPU designer, like you know, those that design CPUs, Intel, Intel design CPUs, and ARM. You know what ARM is? ARM. Have you heard it? Huh? What? So we have Intel. So they design CPUs, right? So what happens is that each CPU has what is known as the instruction set architecture. But for ARM and Intel, these are closed instruction set architecture. So it means that you can only study it, but you can't use it for anything. So once you try to design your own, instruction set, the instruction set architecture, the ISA helps you design a CPU. So that is the CPU itself. It helps you design it. So once you know a CPU's ISA, you can easily design it. What ARM and Intel have done is that they have closed it. They've closed their ISA. You can see it, you can read it, you can understand it, but you cannot design it on your own. You are not allowed. Let me put that. You are not allowed to design it on your own and use it in any way, shape, or form. So if you want to use an ARM CPU or an Intel CPU, you need a license from ARM and Intel to be able to use it. Right? So they will give you the CPU because they design CPUs. They give the CPU and give you the license, and then probably you have to renew the license every year and stuff like that. Right? So this is very not favorable for academia. So if you want to study a CPU and design a CPU on your own, we have to look at an open source kind of ISA. And then we have the perfect one is the RISC-V ISA. So it's an open source ISA designed by University of Berkeley and lab there, right? So they designed it, they made it open source, and then they gave you the ISA to be able to study it. And then once you study this ISA, or once you understand what the test is, you'll be able to design your own CPU with it. They don't care what to use it for. But once you learn the architecture of the ARM or Intel, and then you begin to design it and use it on your own, you might be in trouble one day. They will send their lawyers after you one day. That is if your design become, once you make your design online and stuff like that, right? So the CPUs we design will be the RISC-V CPUs, right? And then, as I said, they have made it open source. You can use it for whatever you want. They don't really care. And then this is the language that the CPU understand, the RISC-V CPU understand. So once you understand this, there is nothing anymore. Right, so I think the last time I explained that once, if you write your C code, right, if you write your C, from your C, you need a compiler, right, to compile your C code because your C code is a high level language, right? The hardware of your CPU does not understand high level language like C. So if you write something like A, B, C, A is equals to B plus C. A code like this, the hardware of your CPU doesn't understand. You need to convert this to something else before you can understand. So you use a compiler to compile this one to assembly language, right? So the assembly language is the language of the CPU or the ISA. So all this you are seeing here are assembly language. So if you want to write RISC-V, if you want to write a RISC-V language, this is what you must use. So again, in the exam, I'll give you the C code, and then I'll ask you to translate those C code to RISC-V assembly language. And then that's what we need to be able to translate it. right? So if you have something like A is equals to B plus C, you need to come and look here and see how it's done. Understood? No. So, bring it, yeah, bring it yourself in your head. So. How? So now, if you pay attention, you will know that you don't really need you don't even need to look at this one. If you pay attention today, you if you don't pay attention, that's when you need this. And then I can bet you that even if you don't pay attention and I give you this shit in there, and you must you won't be able to do anything because you won't really understand what you're doing, right? Okay, so this is the architecture here. I'm showing this thing a lot of times, right? This is the architecture of our Rex 5 CPU. It looks like this. Now the Intel, the also look like this, but each CPU design has these components. It has memory, register file, ALU, PC, all these components. But the way it is arranged, it what makes the difference, right? So the RISC 5 has the way it has arranged it. The Intel ones have the way they arrange this. Then the ARM ones have the way they arrange it. That's the only difference. But the components here are exactly the same. Understood? Right. So now, I believe we can design memory. We know what is inside memory and how to do some operations in memory, right? We know what's inside register file. We know what's inside ALU, right? So number one, like question number one, ALU architecture, draw it. Question number two, register file architecture. Question number three, memory architecture. Question number four, convert RISC, convert C code to RISC 5. Then we get 100%. Probably four. Then some 20 of bits. Eh? Answer all questions. I can't set questions and need to answer some and leave some. I've wasted my time. Answer all questions. So you can't leave any behind. If not, I wasted my time. Like to sit down and set. And then the fact is that the questions I set is not from anywhere, it's just from what you've learned. So I have to sit down and set it on my own, right? Based on what I teach you guys. So there's nothing online. You won't find them anywhere. Understood? Right. So now quickly, right? There's what, as I said, we have control logic, we have register file, we have ALU. Then we have something called the PC, the program counter. I think you know what register file is, ALU is, probably some control logic, just some AND gates and OR gates and stuff like that. But do you know what the PC is? Program counter, right? So now, what happens is that once you write your C code, and then your C code will get translated to the assembly language, and then you need an assembler to convert that assembly language to machine code, right? The machine code will have to be stored somewhere. Where does it store those codes within this architecture? Where? There are two memories. So there are two memories. There's one memory over there, there's another memory over here. Where does it store those codes? The first memory or the second memory? Yeah, the first memory. So the first memory is known as instruction memory. That's where those machine codes are stored. The second memory is known as data memory. Right? So now, once you store your codes or your machine code within that memory, right? You store there's the memory. the memory has kind of data within and it has whatever. So you store your codes here, your machine codes here, right? Then location, we have location 0, 1, 2, 3, going, right? Now, the one instruction is read and executed at a time, right? In the CPU, it reads from the instruction memory, it reads one location, and then that one location is an instruction about what to do, right? So it reads that, it reads one location within memory, execute that instruction, then go back to read again, then go back to read another one. So how does it keep track of which one to read next, right? That is what the PC stores, the program counter, right? That's what it does. So it stores the address of the next instruction. Because if there is no component that stores the next instruction, then what will the CPU read? Where or which location will the CPU read next? Right? To be an issue. So you want to store the next instruction, the address of the next instruction in the PC. So the PC in computing is very, very important. Understood? But the rest of the components, we know what they do, right? Now, your CPU does these four operations, right? And then it does it all the time. This the life cycle of a CPU. Your CPU fetch instructions from the instruction memory, right? Then it decodes those instructions, it executes the instructions, then it updates the PC, then it loops again, right? Fetch instruction, decode instruction, execute instruction, update memory, again, until all the instructions are read. Do you understand? Right. So I think I said the last time that we are studying the IAC, and then what is below the IAC? What is on top of the IAC is the C programs or the Java programs we write. But what we are studying is the IAC, and then what is below it. Not even up to the circuit level. We are studying the IAC, the CPU design, probably the circuit design. You won't go into the chip layout, right? So basically, there are these are the mainstream IACs we have. I talked about the Intel IAC. I talked about the and then the RISC-V. The last one is the RISC-V, right? So each of them has the same components inside it, as I said, but a different architecture, right? Now, we have what is known as the bits. Each IC has what is known as in bits, right? The Intel has 16 bits, 32 bits, and 64 bits. So we always say that the Intel architecture is either a 16-bit architecture, a 32-bit architecture, or a 64-bit architecture, right? For the ARM, we have 32 and 64, right? For X5, we have 32, 64, and 128-bit architectures, right? So what does this bit even mean? What do those bits mean? Hurry up. So if I say the RISC-V is a 32-bit architecture, what does it mean? Or the Intel, the 16-bit architecture, what does it mean? It has what? Store. So imagine that your CPU, your Intel CPU can store only 32 bits of data. How can you run all those software on it? Now, we talked about the register files, right? Right? The data weight of the register file is the what you use to identify your CPU. So if I say a CPU is 64 bits, it means that the CPU, the CPU, each CPU has register file, and then those register file is 64 bits. The data weight is 64 bits. Understood? Now the next is the design type. You have, I think you guys might have seen something like this before, the RISC and then the 6. Have you guys seen that somewhere before? We have two types of CPU architectures, right? We have the 6 and then we have the RISC. You guys have never heard of this before. Okay, the 6 just means a complex instruction set computer. And then the RISC means reduced instruction set computer. Simple as that, right? Now, what happens is that for the complex instruction set architecture, there are so many instructions. For the reduced one, as easy as that, they have reduced instructions, lesser instructions than the complex one, right? So it means that if you have so many instructions, your architecture, the architecture of your CPU becomes very complex. So the architecture is very, very complex because there are so many instructions, right? But for the RISC-V, the Intel has the 6 architecture, the 6 architecture. So the architecture of the Intel CPUs are very, very complex. But the architecture of the ARM and the RISC-V are very simple because they have reduced instructions, very, very few instructions, right? Probably there can be some advantages and disadvantages of each architecture, but you can go and find out what you want, right? Now the type, very important, the type. The Intel has what is known as the register memory type, and then the ARM and RISC-V have what is known as register. Register is the same as load store, right? So what does this mean, right? So if I say a CPU architecture is register memory, right? Register the memory architecture. It means that it can operate on all your CPU is doing. As I said, all the CPUs have this kind of architecture, right? So if I say the CPU is register memory architecture, it means that that CPU can operate on operands, or it can operate on data in memory at the same time. It can operate on data in the register file at the same time. Understood? Now, if I say a CPU is register or load store, it can only operate on data that is in the register file. So if you have some kind of data that is in memory, what the CPU must do is that it must load this data from memory to the register file before it can operate on it. Understood? So you know the difference between the register memory architecture and then the register or the load store architecture. Do you guys understand? All right. Pardon? Yeah, so I said the Intel architecture, Intel, uses register memory kind of architecture. So what happens is that you have register file in your CPU, you have memory in your CPU. You have data, you can store data in both the register file and then the memory. So the Intel CPUs can operate on data, whether it is stored in the register file or in the memory at the same time, it can operate on that data, right? So therefore it is register memory architecture. Now we have the register architecture or the load store is the same thing. That is for the ARM CPUs and then the RISC-V, the ones we are going to see. For that one, it can only operate on data when that data is stored in register file. So it means that if I have some data that is stored in memory, what the CPU must do is that it must first of all load that data from memory to the register file before it can operate on it. Understood? The last one is the Indianness. I think I talked about it the last time. I said we have two types of Indianness, right? We have it's called what? The little Indian and then the big Indian. Or I didn't say anything like that. Huh? I gave some memory architecture and I said if you want to store some data within some memory, it stores it from the beginning or it stores something. I didn't say anything like that. So, yeah? Yeah. So what happens is that the Intel CPUs are little Indian, so you must know what that means. The refined CPU is also little Indian. So it stores data using a little Indian kind of method. Go and find out what that is. Right. Then also go through the rest of the slides so that we can go over next week quickly and discuss the questions. So let's be done for the day. Any question?